you read the question carefully, understand what the question is asking for, and then give us the right solution. Alright? Okay, and the other thing I want to say is, if you have gone through my lectures, usually you know that I cannot think, I cannot process. So when I hear a lot of disturbance, so there was a lot of chattering just now. Actually, I wanted to give up halfway and say that, yeah, I cannot continue. But I guess it's also because you already have a solution, so you are just really speaking among yourself. So I hope it gets better now that we're moving on to this, because you are not going to be given a solution. Yeah, I've checked the lecturers on this course, they don't give solutions, so you're not going to have a solution. Okay, and the only solution that you're going to get is possibly from here. Alright, so now we are on the 2012 paper, and I say that for part of the course, I'll go through question 2, 5, and 6. Okay? So question 2, before I go on, alright, I hope all of you know that you have to answer all questions in section A. So there are 2 questions, one from the digital part of control, and the other from my part. So there are 2 questions in section A that are compulsory. Okay? And choose one question of 2 from section B and one question of 2 from section C. Then altogether, how many marks do you have? There are 20 marks for each question. Okay? So altogether you answer 4 questions. You get 20, you get 18. Alright, and then we'll convert that to 100. Okay? Alright, the next thing you want to take note of is the formula list. So for my part of the course, there's no formula list. Okay, but there's a formula list for this, which applies more to the digital part of the course. Okay? Okay, question 2. Almost the same. Yeah? Okay? Alright. Okay, are you guys ready for me? Yes. Okay. 2A. Alright, let's read the questions. For a closed-loop system with a nominal plant P0, the phase margin of 80 degrees at a frequency of 5 Hz, and the gain margin of 3 dB was derived from the matrix diagram of the gain. Okay, once again, don't have to answer this at all. The question is part 1. By how much can the plant gain increase before the closed loop becomes stable? So we're asking you to convert from dB to a raw value. You understand that? Okay? So 2A part 1 starts at 3 dB is 1.414. Okay? And so thereby gain can increase by 1.4. Okay? The answer? 3 marks. Part 2. What additional delay can be added to a closed loop because the equity is lost? Okay, so this answer is exactly the same as in the sample. So it's conversion of 80 degrees into seconds. So 80 over 360 is 1 revolution. So times seconds means time period. So time period is 1 over 5 hertz. Okay? So if you press your calculator, that's 0.044 seconds. Okay, so therefore, maximum delay is 0.044 seconds. Okay, so there's another 2 marks of verified marks. Part B, show that closed loop control implicitly performs an approximate inversion of plant dynamics, at least for those frequencies where loop gain is high. So part B, the answer for part B is totally in your lecture reading. Alright? So B, closed loop control. Closed loop control meaning a control signal. Alright? Okay, so control signal US. Alright, in your lecture notes you know that this is C over 1 plus Cp of Rs. Okay, because you know that SU is C over 1 plus Cp. Yeah? Okay? And so for Cp much bigger than 1, okay, which is the question where the loop gain is high. So for loop gain is high, US over Rs is approximately T inverse S. Okay? Because when Cp is bigger than 1, alright? This is approximately P inverse, so we have gone into the lecture notes, we have explained this before. And thereby Y is approximately 1. Okay? So this is the answer. Okay? So how do you get from here to here? How do you get from here to here? Anybody wants to know? Okay. Yes, I thought nobody wanted to know. Alright, so U over R, alright, is C over 1 plus C. Okay, sorry. Can you see on the monitor these two screens at the back? Yes. Okay, so this is approximately C over Cp. Because Cp is much bigger than 1, so this 1 is useless. Okay, 1 plus Cp is Cp. Because Cp is much bigger than 1. Okay? And thereby, this is 1 over Cp, and that's why this P inverse is. Then, okay? Alright, because Cp is much bigger than 1, so 1 plus Cp is just Cp. So 1 is useless. Okay, so the C over Cp, cancel the C, we get 1 over 2. Okay, there's another 5 marks. C, consider a state space system. What is controller designed by core assignment? The question says consider a state space system. So what is controller designed by core assignment? At this point in time, don't write me anything about variable time, equations, and blah, because that's for polynomial. Okay? This was state space. Okay, if you write me about variable time, equation, and then you get 0. Alright? So you're supposed to write me in state space context, what is controller designed by core assignment. Okay? And how can it be used to design a state feedback controller? So, if you want the full marks, say that by modifying the values of the state matrix in controller canonical form using state feedback. Okay, we can change the location of the poles from eigenvalues of A to eigenvalues of A minus BA. Okay? So by modifying the values of the matrix, controller canonical form uses state feedback to change the location of the poles from eigenvalues of A to eigenvalues of A minus BK. Okay? And hence change the dynamic behavior of the system. Okay, so this is part one of the solution. Part two, okay, you're supposed to tell me that U is minus KX. Okay, and this method is called closed loop pole assignment, where the closed loop poles can be arbitrarily assigned by reading that the state X, okay, through a suitably chosen constant in vector A. Okay, and that is whole thing explaining U equals minus K X. But if you write me U equals minus K X, you get nothing. Maybe you get half a mark or now. Okay, so it doesn't write over, right? Then you get 5 marks. Okay? And these are actually in your slides, the 2 slides that I spoke about in the lecture. Okay, so let's move on. It's difficult to manage, and some of you can talk faster and some of you can slower. But really, there's no need for you because it's in the lecture, okay? Okay, so let's move on. D. What is controllability in the context of state feedback control? And what is meant by stabilizability? So you are supposed to memorize this and give us a whole solution in sentences. Okay, so controllability, similarly, is all in the lecture notes. Definition, okay, just tell me that the state X0 is said to be controllable if there exists a finite interval 0, t and an input ut such that xt equals to 0. Okay? And then if all states are controllable. The system is completely controllable. Okay? If the uncontrollable subsystem is stable, the system is stabilized. Okay, that's what we're asking for. E. Okay. What are the components of a PID controller? And then gives the control law in time domain and the plus domain. Okay, so time domain, all are the components which tells that they are proportional, integral, and derivative terms in a PID controller. Time domain. Okay. What's wrong? No, derivative. Okay. Terms in the PID. Alright? Time domain control law ut a 1 plus 1 over ti how plus t dot. Okay? And the plus domain US A A plus A over TIS plus A ES. Okay, so question 2, there's 20 marks, and question 2 is a compulsory question. So if you cannot memorize any of this, then you basically have 0. Question 2.